All right, so here we're going to continue talking about, well, non-planar graphs. We're going to look at how to determine whether something is something versus planar or non-planar, right? So we have Euler's formula, and that is a way to relate the vertices, edges, and faces of a planar graph, and we're going to use that to kind of take a step further, right? It's a starting point to prove that something is not planar by assuming that the Euler's formula has to work and then arriving at some kind of contradiction for it not working. All right, now here, so here's a complete graph, right? So the graph that we see here is K5. So here, let me write that down. So we're going to take a look at this graph K5. Right now, the complete graph means that every vertex, all right, has an edge to all the other vertices in the graph, right? So as you can see here, right, there's 5 vertices total. So each vertex here has 4 edges coming out of it, right? Because it's going to the other vertices, right? And we're proposing here that this is non-planar, right? That there's no way that I can place the vertices to make sure that the edges are not crossing. All right, so that is my proposition here. Right now, right, it's really just by trial and error, but how do I know that I'm just not trying the correct placement of them? Right, so we will actually give a proof here of how we would arrive at something like this, right? And we'll also take a look at K5 and also K3, right? The bipartite graph. So here, so when I mean K3, here we have 3 nodes and 3 nodes here, right? So in this case, 1, 2, 3, those nodes, there are no edges between those 3 nodes. And then 4, 5, 6, there's no edges between those 3 nodes as well, right? Hence the 3, 3, right? This one is a complete bipartite in the sense that the set of 1, 2, 3, each vertex here goes to the other 3, right? Or vice versa, however you want to think of it. And again, the notion here is that there is no way that this is planar, all right? Okay, so I am going to arrive at that notion. Again, a reminder, right? Euler's formula is the vertices minus the edges plus the faces is equal to 2. All right, now we're going to know what the how many vertices and edges we have, right? Because we have a visual of the graph. All right, the notion here is, well, I have this equation and I want to determine, right, how many faces it should have, and come to a conclusion that that is going to be impossible based on the vertices and the edges. Right now, before arriving or before kind of setting off on that path, let's take a look at, right, when we're dealing with, let's say, a bipartite graph, right? So here, say something that looks like this. All right, now connect these vertices. Okay, so the goal here is that, all right, we can move the vertices here to have a planar graph. Now I want to define the girth of these planes by how many edges it takes to surround the face here. All right, so in this case we could see that it takes 1, 2, 3, 4 edges, right? And that is the same for this face here, right? And also the same on the outer one, right? You got 1, 2, 3, 4. All right, so it'll take at minimum 4, right? I can't do it with 3 because of the nature of the bipartite graph, right? If we recall like this, right? There's no, since these are connected, right, the minimum connection is going to be 4, right? And also notice when talking about these edges, the edges that surround the face are doing double duty, right? Because if we look at this one that is encapsulating here 1, 2, 3, and 4, right? These outer edges also are bounding the edge on the outside, right? The outer face here. Okay, so here, let's draw that here so I can, so it looks something like this. And if I call this F1, F2, and then the overall bigger one, F3. Right? And we're define the girth, right? Or how many edges it takes to encapsulate a face. It has to be equal to 4, right? So we'll just say G is 4, right? And not only that, right? So the edges are doing double duty in the sense that here we have, I use the edge twice here for, let's say, F1 and F2, these inner edges here that run from here to here, right? I think of them as counting twice when trying to figure out how many edges do I need to surround a particular face, right? So that is for a bipartite graph. Now, when we just have a connected graph that's not bipartite, right, so for example here, like let's take a look at a graph like this. All right. All right, so we actually have, there is a minimum number. So this works, right? It's still 4, but the minimum is actually 3 if we think of this for just a regular planar, a planar graph that is not bipartite. All right, where if you look here, right, the girth of this is 3 because we have these edges here, right? 1, 2, 3 to surround the face. And it's doing the same thing here. The edges are doing double duty because here we could see the edge from 1 to 4. I count twice depending on which face surrounding, and then also the outer edge. That one is getting like it's surrounded by 4, right? The outer edge we're living in the plane here. So the girth for something that is connected but not bipartite is going to be 3. All right, and in general, the girth times the number of faces must be less than or equal to 2 times the edges, right? Because we're counting the edges twice, right? For each face that it's being surrounded, that is surrounding. Okay, so the goal here is I'm going to know how many edges, I know how many vertices, right? And using Euler's formula, I have a theoretical possible number of faces. And based off of that and this inequality, right, I'm going to arrive at a contradiction to show that I get something that doesn't make sense. Hence, that proves that the graph is not planar. So now let's go back to establishing K5 being not planar, right? So again, K5 looks like this. Okay, so looking at this, we have 5 vertices, right? So each vertex has 4 edges, but we're double counting them. So here, vertices, excuse me, vertices is going to be 5. It's going to be 5. Edges, excuse me. Edges is going to be 5 times 4, but each one of them has 4 coming out. But again, that's double counting since they're undirected. So edges is going to be 10. Now Euler's theorem says if this were planar, right, then here we have V minus E plus F must equal to 2. So that means the faces must be equal to 7. All right, it has to, right? If it's planar, it must follow that equation, right? V minus E plus F equals to 2. All right, so since this is just a connected graph, simple graph, not bipartite, then the girth here, so G, so I'm going to go back to this, it must also satisfy this inequality here. G times F is 2E, all right? So here at minimum, I need 3, you see here, 3 edges to surround a face at minimum, right? I mean, it may be more, but that's the minimum that I need here. So G being 3 and then F being 7, that gives me G times F to be 21. All right? Yeah, because every face needs to be bounded by at least 3 edges. All right, it could be more, but minimum 3. All right, but I also know that the edges are 10. So if I double them up, right, then 2 times E is 20. And arriving at my conclusion here, the girth times the faces must be less than or equal to 2E. Well, I arrive at a contradiction. G times F is 21, and that is indeed not less than or equal to 20. So this being not true, so what that tells me is that K5 is not planar. So indeed, I can confirm, right, from what I was previously doing in trying to see if I could configure the vertices in a proper manner, that I cannot do that so that none of the edges are crossing. Okay. All right, let's do one more example here. All right, so let's take a look at the graph K3, 3. All right, so we're looking here at a bipartite graph here. There we go. All right. And what we can see here, again, what makes it bipartite here is that we have these 3 vertices, 1, 2, 3, and there's no connection between the 3 vertices here and the 3 vertices up here, 4, 5, and 6. Now, complete in the sense that the vertices 1, 2, 3, each one of those has an edge going to the other 3, 4, 5, 6, right? 1 goes to 4, 5, 6, 2 goes to 4, 5, 6, right? Hence my bipartite, right? Where we have 2 sets. Here the set is the vertices 1, 2, 3, and the set 4, 5, 6. And there's no edges between the ones in the set 1, 2, 3 and the set 4, 5, 6. All right. Now, if we again trying to prove that it's not planar, we see, all right, V is 6. Edges are again 9. All right, we can count those up. Each one of them has 3 coming out of it. Okay, so that gives me 9. And then Euler's formula gives, so V6 minus 9 plus F equals to 2. Solving for F, we see negative 3 plus 3. Faces must be 5. Now in this case, the girth, since it is bipartite, has to be minimum 4 here. All right. Okay. Minimum 4 right here. And again, if we try to move these, since there's no connection between any of these vertices up here, all right, I can't do it with 3. It has to be minimum 4. Okay, so that means that knowing that G times F is going to be 20. Now, twice the edges, if this were planar, right, the edges would be doubled up in surrounding a face. That would be 9 times 2, which is 18. And now again, we arrive at taking a look at this inequality here. We get 20 less than or equal to 18. Again, not true. So what that tells me now is that Euler's formula does not work. Hence, K33 is not planar or non-planar. All right. And in general, we want to take a look at, given a graph, right, to show, we want to take a look at this inequality. All right, the girth, if it's a bipartite graph, right, it's going to be 4, right? If it is a just a connected graph, right, then it'll be 3. Okay? All right.